extensive properties, the amount of what you have matters. They're basically measuring the amount. So things like, we could say, how much does it weigh? How many moles are there? Or what is the volume? But there are some other properties that are also linked to how much are there. In particular, one we'll talk later in the semester about is energy. So if you think about if there was a drop of boiling water that hit your arm, it would probably hurt, but other than that, you would suffer no ill effects. But if you suddenly fell into a pot of boiling water, then you would probably die. So the amount of boiling water matters for the energy that your body absorbs. So this one is also an extensive property. With an intensive property, then the amount doesn't matter. So here we are looking at only the material, so what it is, say water, and the state. So the state might be something like, is it a solid, a liquid, or a gas? Or it might be, is it 100 degrees Celsius or is it 0 degrees Celsius? So water at 100 degrees Celsius, yes, that's problematic. Water at 25 degrees Celsius, not so much of a big deal. So only those matter. So if we look at things like color and temperature, those are intensive properties. We're not going to focus on those though. We're going to focus on the ones that are ratios. These are ones that are this much per this much, and usually it's comparing two of these things over here. So what mass per moles? What mass per volume? Okay, those are things that we can use when we're doing conversion. So these are mole train tickets. And get us from one of those places to the other. So we've already talked about molar mass. Density would be one. How many grams per volume something is. If I look at lead or gold, it has a lot of grams per volume. But if I look at air, not very many grams per the same unit volume. And then we have concentration. So for concentration, we actually have lots of ways of measuring this. And so I'm going to list some of those ways here. We are just going to focus on molarity. Now we have already looked at percent composition, percent by mass. So I can look at just one compound that may be sodium chloride. What percent is sodium? But I could also look at a mixture and say, oh, if I have salt water, what percent of that whole solution is made up of just the salt? So which one we use depends on what the context is. If I'm working in the chemistry lab, percent composition isn't real helpful. But if I'm working in industry, it's a lot easier to weigh things out by mass. And so using percent mass might make a lot of sense. So if you go and buy vinegar, vinegar is just two chemicals. It's water and acetic acid. They're going to list on there what the percent is, and that's going to be the percent by mass, because it's a lot easier to go and say, oh, I have this many kilograms that I dropped into the vat and that many kilograms that I dropped into the vat than it is to calculate how many moles. We could also have a mole fraction. Molality. Or we could do, you've probably seen parts per billion, parts per trillion. So ppb, ppt. On those, we're not going to worry about them right now. Mole fraction will come back when we get to gases. Molality will come back next semester. But the one we're going to work on for right now is molarity. And molarity is measured as moles of solute divided by liters of solution. So most of these, kind of like a percent, are part on top, whole on bottom. Everything is on the bottom. One of these does not do that. We'll worry about that next semester, but much like a percent, the part that I'm looking at is on top, and then everything all together is on the bottom. So not just the liters of what we dissolved it in, but the liters after I've mixed everything together. So we often use units of moles per liter. We can use M to mean the word molarity, which is what we're measuring, or the concentration, or it could mean moles per liter, the unit. Okay, so we don't usually use grams for both what we're measuring and the unit. We'd say we're measuring the mass and the unit is grams, but in this case, both of them are the same thing. So you'll see examples in just a minute. When we use it as the unit, we use the word molar. Molar. Okay. So you'll hear me say that as I do some examples, and then I will. Where was it? All right, so let's do an example. If I have a 1 molar, so I would say this is 1 molar HCl solution. I pick up a bottle in the lab, and the bottle is labeled 1M HCl. What that means is not how much is in there, but for that concentration, every liter contains 1 mole of HCl. Okay. So if I had half a liter, then I would have half a mole. And if I had 3 liters, I would have 3 moles. So the ratio goes along with it. Now we do have to be cautious for ionic compounds, because an ionic compound tends to separate in solution. And I will say that usually, almost all the time in general chemistry, our solvent is going to be water. And so we would indicate that by saying AQ for aqueous, okay? But if you don't see AQ, you just sort of assume it's dissolved in water, okay? When you get to organic chemistry, there are lots of different solvents you might use, but this year, everything's dissolved in water unless we tell you otherwise. Okay, so for ionic compounds, ions separate in water. So a 1 molar solution of CaCl2 every liter contains 1 mole of Ca2 plus, okay? And those ions, which would be like an atom with 2 electrons ripped off, are completely surrounded by water. There's no chlorine touching it at all. They are completely separated from the chlorine. And instead of 1 mole of chlorine, since I have a 2 here, those are going to separate too. They're not going to walk off in pairs. They're going to be separated. And so I will have 2 moles of chloride ions. So completely separated from each other. And then if I wanted to talk about the ionic strength, how many ions there were, altogether I'd have 3 moles of ions in that solution. Okay, so that's just a side note about ionic compounds. We're not going to worry about that too much right now. I'll just mention it when we go through calculations that involve ionic things again. Okay, now let's look at what if I had 15 moles of HCl dissolved in 6 liters of solution? So enough water to make 6 liters of solution. I'm just going to say in 6 liters of solution, your active chemistry homework will generally say dissolved in enough water to make. Don't let those extra words confuse you. It's 6 liters of solution. They're just trying to be very accurate by not saying it's not dissolved in 6 liters of water. However much water there was, which was probably pretty close to 6 liters, the final solution was 6 liters. So they're just being technical about it. It's kind of like my dad is a biology teacher, and like if you use tortoise instead of turtle in the wrong spot, he'll call you on it. But like we all know what we mean, right? Okay, so 6 liters of solution. Okay, so what are we going to do? Our formula is molarity is moles per liter. This isn't hard, so we just look for the moles. 15 moles divided by 6 liters. And that works out to, what was that? 2.5. So I have 2 sets of units here. I can use both of them, kind of like with density, you often say grams per milliliter or grams per centimeter cubed. So we could say mole per liter. That's perfectly fine. To make things easier when typing or when labeling things, we might also say 2.5 capital M. That means 2.5 molar. Okay, these are identical to each other. All right. Now, when we measure things in the lab, we don't typically use these units though. If I were going to go and measure the volume of something, I'd probably grab a graduated cylinder. And in your drawer, you have 10 milliliter graduated cylinders, and you have 25 milliliter graduated cylinders, but you don't even have a 1 liter graduated cylinder, right? 1 liter would be a beaker that would be like this big around and this tall. It wouldn't really fit in your lab drawer. So we usually measure in milliliters. So we have to be able to go back and forth between milliliters and liters. There are lots of tricks to do this kind of thing. So I'm just going to highlight a couple of them, but I will almost always use a fraction because I find that's the most consistent way I can be with converting anything. But one common way to do this is to look at all the possible prefixes you might have. So mega, kilo, no prefix, milli, micro. And if we're at milli and we're trying to get to no prefix, then we'd have to move over 1, 2, 3 times. So that means I'm going to move my decimal over 3 times. So if I had 250 milliliters, then what I would do is, I don't have a decimal expressed, but I would know where that decimal point would be if it were expressed. I'm going to move it over 1, 2, 3 times. 0.25 up. Oops, 25. Okay, why did I get rid of that 0? How many sig figs does this number have? Just 2. This 0 is not significant without a decimal point. So when I do that conversion, I need to leave it off here. Now, is this 0 significant? The left-hand 0, so it is not significant. Is it important? That one is debatable. Most of the time, zeros are important, but it's not telling us anything about the precision. A 0 here would tell us we know it more precisely than we do. Okay, so this is liters. The way I would do this with fractions is I would say 250 milliliters times 1 liter over 1,000 milliliters. Now, generally in chemistry, it's just these that we go between kilo, nothing, and milli. And so we're always moving by 3. There are a few times we would go by others, but we're always moving by 3. So when in doubt, just move the decimal place 3 times. You've got a 50-50 chance doing that right. Okay, so if I have this fraction, where do I put the 1,000? Well, I have to think to myself, a milliliter, that's the size of the tip of my finger or a miniature marshmallow, and a liter would be like a big gulp drink that I might get. Do I have 1,000 miniature marshmallows in one big gulp, or do I have 1,000 big gulps in one miniature marshmallow? Right, so the 1,000 is going to go with the smaller unit. Okay, this is going to give me the same thing, 0.25. So two ways that we can go to liters. All right, if we have moles, we don't really have a device in the lab that I can go and scoop out something and say, how many moles is this thing? We usually weigh it and do mass, but we already know how to go mass to moles. So let's look at an example that involves mass in milliliters. Okay, so here's an example problem. If 100 grams of HCl are dissolved in 750 milliliters of solution, what is the concentration? Well, the concentration is measured in molarity. So let me put that here because in theory, we could have lots of ways we were measuring that. We know molarity is going to be moles over liters, but we don't have either of those yet. Okay, so let's take our 100 grams. How many sig figs on that 100? So I do have the decimal here. So are these zero significant? Yes, so 3 sig figs here. Okay, in order to get to where I want to go, I want to go to moles. Now I got to get on the mole train, okay? And to get on the mole train, I need a ticket that tells me where I'm coming from, grams on the bottom, and where I'm going to, moles. And I need to think to myself, okay, of these ratios, let's see, molar mass, density, and concentration, which one has units that include both grams and moles? Molar mass. So I'm going to do the molar mass. So I'm going to go to the periodic table. I'm going to look at hydrogen as 1.01. I'm going to look at chlorine is 35.45. And so this is going to be 36.46 moles. Nope, that's not how many moles. There was only one mole. The number has to follow the grams. 36.46 grams, and there was only one mole. Okay, let's plug this in. This has 4 sig figs. This one has 3 sig figs. How many sig figs should I write in my answer? Just 3, the smaller number. Okay, so I plug that in and I get 2.74 mole. Now I want to keep track of what I'm talking about because I've got a mixture here. I don't want to mix up in my head. Am I talking about the water? Am I talking about the hydrochloric acid? Am I talking about the solution? So this is just the HCl. And if I want to clarify what it's dissolved in, then I can say it's aqueous. But the HCl itself is only this many moles. Okay. Now I need to do a similar conversion for my milliliters. So I have 750 milliliters. I'm going to do the same thing I did over there, 1 liter over 1,000 milliliters. Now notice here, I have the 1,000 with no decimal. Okay, remember, whenever we do a conversion in the metric system, those are exact numbers, infinite significant figures. So this is not going to change how many sig figs I have. This isn't a measurement, this is a conversion. Okay, lots and lots of sig figs on this. All right, so this is going to give me 0.75. Okay, how many zeros am I going to put after that? Any? None? None, because I only have 2 sig figs here, so I'm only going to write the 7.5 there. Okay, so this is liters, and then I do this division, 2.74 divided by 0.75. And I plug that into my calculator, and I get something that looks like 3.658 and some other numbers. How many of those numbers do I get to keep? So my top number has 3 sig figs. My bottom number has 2. So I'm only keeping 2. So I'm going to call this 3.6 capital M molar, or I could say moles per liter, either way. I'm sorry, what was the question?
When you round 6
from here, so that 5, my rule is you can round it up, you can round it out. I don't care. Technically, the rule is round it so the last number you write is even. So in this case, since that's a 6, I'd just drop it.
Oh.
But if you rounded it to 3.7, I wouldn't care. Okay. There's my answer. All right. So if I need to make something in the lab, that's what I can do. Now, unfortunately, HCl is a gas, so I probably wouldn't weigh that out on a balance. But if I took some other solid, sodium chloride, something like that, I could weigh it out on the balance and then dissolve it. Now, every lab we do that involves hydrochloric acid usually has some different concentration we need. Sometimes we need really concentrated 12 molar HCl. Sometimes we just need 1 molar. Sometimes we only need 0.1 molar. And it doesn't make a lot of sense for us to have all of these different bottles in the lab. So we usually just keep the most concentrated, what we call stock solution, and then dilute it down, okay? So in order to know how to dilute it, we have to know how many moles we're putting into this. So we need to be able to go from a volume to moles. So if we have molarity is moles per volume, and sometimes I'll put a little L here just to remind ourselves that that has to be in liters. Don't let that confuse you. I'm just saying don't put it in milliliters. Remember to convert, okay? If I just want moles, I'm going to rearrange that equation by multiplying both sides by volume, and I'm going to get MV. Okay? So any solution, I can figure out how many moles I have by MV. All right, so for a dilution, generally use very precise glassware, and I can know really, really precisely what my volume is with this. But I'm going to start with some smaller amount here. So let's say this is going to be my 3.6 molar HCl, so I'll just label that. All right, so that's what's down here is the 3.6 molar HCl. And to dilute it, what am I going to add to it? Just water. So am I adding any more HCl? No. So the number of moles of HCl isn't going to change. It's going to stay the same. The concentrated will have the same as the dilute. Okay? So moles of concentrated is equal to moles of dilute. Right? And since I know moles is equal to MV, I can say the molarity of the concentrated times the volume of the concentrated is equal to the molarity of the dilute times the volume of the dilute. I'm not changing how many moles there are. Now, when I use this glassware, this is called a volumetric flask, it can really only measure one thing. If I try to measure 50 milliliters, try to measure 100 milliliters, it's not going to be able to do any of it because it doesn't have lines on it. It just has this one little ring up here, and that's going to be for whatever that flask is. So in this case, it's going to be a 200 milliliter flask. Okay. So what is the concentration of a solution paired by diluting 50 milliliters of 3.6 molar HCl, 100 milliliters. And this is a dilution problem. Okay, so I'm taking a stock solution that I had some 3.6 molar, and I'm going to dilute it down. So I'm going to use this formula here. The MCVC is going to be 3.6 moles per liter times, now it's not 50 milliliters, or it's not 50 liters, it's 50 milliliters. So we're going to have to divide that by 1,000. Yes? This is an L. This is an L. Okay, so this 0.050 is just me converting milliliters to liters. Okay, so I'm going to multiply that out, get 0.018. I only have 2 sig figs, moles HCl. I'm running out of room down here at the bottom, so I'm going to switch over here. So this is going to be equal to MdVd. So that's the molarity of the dilute times the volume of the dilute. And we know that volume is 200 milliliters. But we can divide that by 1,000 milliliters to make it liters. Okay, so that's going to look like 0.2000 liters. 0.050. There's a 0 in here. Okay, so this should be 1/8. Let me double check. Yep, that's what I get to. Let's do our math right. That's what happens when I try to do it in my head. Use your calculators, people. Okay, how am I going to get this by itself? Generally with this kind of thing, I want to get the letters by themselves, put all the numbers together. So algebra tells me the golden rule is do unto one side as I do unto the other. So what am I going to do unto those sides? How do I get division? Yeah, I'm going to have to divide both sides by my 0.2 liters. And that's going to cancel. And the molarity of my dilute solution is going to be that divided by that, which I think works out to be 0.9. And then my units, moles per liter. But don't do things in your head, people. Okay, yes. I've run into a problem. My calculator is not as smart as me. I had 2 sig figs here. I have 4 sig figs here. How many sig figs should I be reporting? Smaller number, 2. Is this significant? No. So I have to be smarter than my calculator and put a 0 in. So if the calculator's not reporting enough, after the decimal point, add enough zeros to get to the right number of sig figs. Okay. So we'll do some more examples on Monday, but those are our basic calculations for concentrations. Okay.